I have you loud and clear.
Hello. Welcome. Science.
And that is to say,
physics,
medicine,
nature,
or
space, time,
the brain,
life, the universe.
Hello, this week from posters to pancakes, how do the objects that we see around us every day actually get made? We're uncovering the science of manufacturing, from the very, very big to the very, very small and the very, very complex.
Plus in the news, how pesticides are affecting bees and using AI and drones to keep tabs on ocean health. I'm Georgia Mills.
I'm Chris Smith, and this is The Naked Scientists.
The Naked Scientists podcast is powered by ukfast.co.uk.
Cancer is one of the biggest killers in the developed world, and the later it's detected, generally, the worse the prognosis for the patient. So being able to spot cancer sooner is a major priority for researchers and doctors. And a team from the Cancer Research UK Cambridge Institute have now developed a new blood test that can track down up to 8 different cancer types. James Brenton from CRUK is with us to explain how it works. Now, James, we're familiar with the idea that cancer generally starts in a tissue somewhere. So what's the blood got to do with this?
Well, one of the biggest advances in the past 10 years is the realisation that we can detect the faulty DNA that's inside cancers in the bloodstream. And that can be used as a non-invasive liquid biopsy test to try and pick up cancer either in patients who have it or potentially as an earlier diagnosis method.
So when a person has cancer in any part of their body, the abnormal cells there are spilling DNA over into the bloodstream, and that's what you're saying you can go for?
That's right. In fact, this is a very interesting part of the process which we don't fully understand. As cancer cells die, they release their DNA into the blood. That means you can detect it in the blood. The problem is that our blood has got DNA from normal cells in it, particularly from the white cells in the bone marrow, and this is in a huge excess compared to the amount of faulty DNA that comes from the cancers.
So you're literally doing a DNA needle in a haystack,
Absolutely.
in a giant DNA haystack.
And in fact, the advance we've done is to guess that perhaps there might be specific size differences in the DNA from the cancer as opposed to the normal DNA.
What do you mean by size differences?
So we know that DNA from normal cells is about 166 base pairs long.
Genetic letters.
Indeed. So the size of it is a very specific size. But then if we look at DNA sizes from cancer, these sizes are significantly shorter, between 90 and 150 base pairs. That's, again, the unit size of a piece of DNA. And so our advance is really by using a very cheap test, we can significantly improve our ability to detect that DNA by pulling out specific sizes of the DNA from the blood.
Just summarising then, so basically if I take a blood sample from me, I assume I don't at the moment have cancer, and you look at the DNA that's floating around in my bloodstream, you will see fragments of the DNA that's come out of dead or dying or lysed cells, and on average it's going to be 150 or so genetic letters long, those bits. And you're saying if I had cancer though, you'd see another population of bits of DNA there which were much shorter. Do you know why they should be much shorter?
So we know that when normal cells die, the DNA in those cells is broken up by a process called apoptosis. And that's a programmed way in which the cell breaks down all its components for recycling. And because the enzymes that break down the DNA work on particular sizes, because the DNA itself is very, very long and it's wrapped around large proteins, what happens when those normal enzymes, the sort of turnover engines of the cell work, they chop it down to 166 base pairs or thereabouts. However, in cancer, those processes may be slightly different, and that's because the DNA in the cancer has got different marks on it. That's called methylation, and that may affect the way in which that DNA binds to these proteins, the nucleosomes that are responsible for protecting it in a normal cell.
And how good is this as a test?
So you talked earlier on about a needle in a haystack, and that's really the problem that we have in front of us. We can detect with normal methods of sequencing the DNA probably down to about 0.5% of DNA if it's cancerous. With these new methods of essentially pulling out specific sizes, we can increase that by over twofold in at least 95% of cancer patients and over fourfold in about 10% of patients, with very significant changes in some patients. So those differences make a huge difference to picking up very important changes in the cancer that may be responsible for changing treatment or for picking up a cancer early.
So you could use it either as a diagnostic screen. You could just screen people's blood to see if there's a cancer there in the first place, but equally you could use this if I'm on treatment, for example. You want to keep an eye on me to see if I've responded, and if I've continued to respond or if my cancer's coming back. It would be a sensitive way to get an early warning sign.
So that's exactly right. So we've shown that using this cheap method means we can pick up a cancer recurring earlier than other methods of trying to detect this circulating cancer DNA. So that means that for the patient, there may be earlier options, or the patient may be better or fitter when we start treatment.
And which cancers? I mentioned earlier you said 8, but which cancers are you going for with this?
One of the important advances is that our method also improves detection for difficult to detect cancers, particularly those associated with brain cancer, pancreatic cancer, renal cancer, and ovarian cancer.
So these are things that tend to present late, aren't they? Cancers we pick up when often they're quite advanced.
They are, and many of those cancers don't have easy ways of using other methods to detect or screen for them.
Is this test ready to go now, or is this at the very early stages?
So I think the methods we've now discovered are applicable by everybody around the world. You don't need expensive methods to apply it. And I think what we'll see now is validation, in other words, testing our methods in other people's studies to show that it works and bring it into the clinic.
Sounds terrific and important in equal measure. James, thank you very much. That's James Brenton. He's from Cancer Research UK and Cambridge University.
Now feast your ears on this. If you were to stick a microphone into the water in some parts of the Indian and Pacific Oceans, alongside the snapping sounds of prawns, you might hear some munching and squeaking noises. The animals responsible are dugongs. These are also known as sea cows, and these are marine mammals. They weigh in at over 1/4 of a tonne, and like their land-dwelling counterparts, they also eat grass. In this case, though, it's seagrass. And dugongs are a very useful indicator of the health of their local marine habitat. Amanda Hodgson at Murdoch University in Perth, Western Australia, has just won a $250,000 Google Impact Challenge Award for her work. She's using drones and artificial intelligence to count dugongs all over the world. And she told Chris why this matters.
Dugongs feed exclusively on seagrass, and they actually occur throughout the whole Indo-Pacific. But unfortunately, they're vulnerable to extinction, largely because their seagrass habitat is disappearing. And that's something that we should all be very concerned about, because we all need seagrass. Seagrass feeds 3 billion people and also is extremely good at storing carbon. Probably people don't realise just how vital seagrass is, because it plays a part in a lot of species' life cycle. So even things like prawns, which a lot of us love to eat, seagrass is essential. So without seagrass, we wouldn't have prawns.
So we can try really hard to save dugongs, but if we don't save the seagrass, then we've got no dugongs anyway.
That's exactly right. Yeah, so really our idea is basically to be getting people's attention on dugongs, because dugongs are an excellent barometer for seagrass health. So if you don't have seagrass, you don't have dugongs. So you know if the dugongs have disappeared, you should start worrying about the seagrass.
So how are you approaching this? I mean, how are you going to tackle a problem that's not just one little geography? This is a worldwide problem.
Yeah, it's really difficult, because the best way for us to monitor dugongs is to do aerial surveys. And that traditionally has meant putting a team of 5 people in a very small plane, flying very low and very slow over hundreds of kilometres. Quite risky for that team and very expensive, and it requires significant expertise. And all of those things don't occur in most of the countries where dugongs occur. So to overcome that problem, we have been developing methods for using drones instead of planes to do the surveys. So just basically using drones to take aerial photography of the ocean and then counting the dugongs in the images.
Have drones got the range, though? How big are these drones?
So I originally have trialled some pretty high-end drones, the same drones that the military uses, and they work very well. They have the range and the endurance, but they're not within the research budget of most people. So really, large-scale surveys, we really need some new cheap drones to be developed that can have the same capabilities. But we're also developing methods to do more small-scale surveys, and in a lot of areas, actually, the dugongs occur in quite small pockets. So using drones that are off the shelf that people in developing countries can afford and have access to, and we're developing methods to use those so that it's really simple and user-friendly.
So how will it work then? You'll deploy some drones to a geography. They'll do the aerial survey, take photos, and what can you extract from the photos? There's a dugong.
Yeah, so that's the tricky bit. Originally, we were having to just review the images ourselves, which takes a long time. So what we've done is developed our dugong detector, which uses artificial intelligence or machine learning to pick the dugongs out of the images automatically. And so that has reduced the time it takes to review the images by 95%.
How do you know you're not spotting the same one multiple times? If there's the sort of Where's Wally of the dugong world where it keeps popping up all over the place, how do you know you're not just double counting?
Well, that's all part of the survey design. So we have to make sure when we design the survey that we're designing in a way that we're unlikely to come back and see the same animal again. And we're actually usually sampling an area rather than covering the entire area. So we maybe survey 10% of the area we're interested in, and then we extract from that an estimate of how many dugongs there are.
And have you got a sort of back end for all of this, so all the data coalesces so that then you can bring together all of the different sampling sites around the world so you get a more global picture?
Well, that's exactly our mission at the moment. So our vision is to create a dugong detector online hub, which would support people doing these surveys all over the world. So they would have access to a tool that would help them design their survey and choose the appropriate drone. And then they would download the dugong detector, which would process all the images for them. And we're going to expand the dugong detector so that it also classifies the images according to the environment that you can see in the images, including the seagrass that you can see. They will then upload all of the data from the dugong detector to an interactive map on the hub, and they'll be able to create their maps, but also to a global database.
So it's got benefit for keeping eyes and tabs on dugong numbers and how they're getting on in the environment, but then it's a proxy marker for probably the environmental health in those regions, isn't it?
Yeah, absolutely. So if you're able to do some surveys regularly and you know the dugongs have always been in this area but suddenly they've disappeared, then that's a warning, basically, if you need to go and check what's happening with the seagrass.
And does that mean then that you can then spot areas that are either very good, and so you can then ask, why are those areas so good? And equally, you can spot areas which clearly show a downward trend, and you can ask, well, what's different? And why are they showing a downward trend? So you can begin to tailor your interventions a bit more.
That's exactly right. Ultimately, it gives local authorities in the areas the ability to know what are the areas we really need to protect and what are the areas we really need to focus on to mitigate any impacts on the dugongs and the seagrass.
Amanda Hodgson from Murdoch University and winner of a Google Impact Challenge Award from earlier this month.
And actually, Amanda's written us an article which tells you a bit more about the work, and there's some lovely pictures there as well. You can find that at nakedscientist.com/articles if you want to check it out. On the way, the impact that pesticides have on bees inside the nest, which we didn't know before, and also how manufacturers are now 3D printing parts for jet engines. Before that, though, are you able to bounce out of bed in the morning and to greet the sunrise? Or are you more like me and Georgia, and it really is an uphill struggle to force yourself into the land of the living every day? That's definitely you, isn't it, Georgia?
Oh, absolutely. I have about 14 alarms on my phone to get me out of bed.
I have about 14 cups of coffee to get me going in the morning. But it turns out that whether you're a morning-loving lark or a darkness-craving night owl can have very far-reaching effects on your health. By studying data from 500,000 individuals, researchers at the University of Bristol have found that women who are morning people have a much lower risk of breast cancer than those who aren't. But why? Talking to Adam Murphy, Rebecca Richmond.
So of interest to our particular study was looking at sleep characteristics in relation to breast cancer risk. And we looked at 3 specific sleep traits of interest. So one of those was an individual's preference to be a morning or an evening person. A second one was we asked individuals about how many hours of sleep they were getting each night. And finally, a question also asked about insomnia risk, so that's difficulty getting to sleep or waking up in the night. In these two large studies, we looked at these questions and we also looked at genetic variants which were associated with these various sleep traits and looked at the contribution of these towards risk of breast cancer. What we found was individuals reporting to have a preference towards the morning were actually protected against risk of breast cancer.
How much were they protected by?
In terms of looking at the extremes, so definite morning people versus definite evening people, there we actually showed a 40% reduction in risk of breast cancer.
Well, that's a fairly massive reduction for something as taken for granted as sleep.
Yeah, so it's quite interesting findings. I suppose we have to also put this in some context in terms of actually looking at absolute risk. So these 40% estimates are relative estimates. In terms of a bigger perspective, we know that 1 in 7 women will develop breast cancer at some stage during their lives. So it's really important to recognise that although sleep may be one potential modifiable risk factor, actually there are some other very important risk factors which we know about. So it's very important to, for example, maintain a healthy weight, to not smoke and to drink in moderation. And so at this stage, it's quite early findings with regards to the actual impact of sleep on breast cancer. But this work goes some way towards putting sleep on the research agenda for breast cancer.
Do we have any idea why preference for sleep time is a factor in this?
So it is quite complicated to think about what it actually is about being a morning person that protects these women. And in terms of potential mechanisms, one quite well-known hypothesis is regarding an effect of light at night, which might be a potential indicator as to why those individuals who reported to be evening people were more at risk. So the idea behind this light at night hypothesis is that individuals who stay awake later into the evening have more exposure to artificial light, and that this can cause disruption in hormone levels, which might put these women at risk. Some other potential links between morning and evening preference and breast cancer relate to potential differences in metabolism and also differences in other lifestyle behaviours.
Does it imply then that shifting your behaviour, shifting when you sleep would help, or is it a genetic thing that we can't really affect?
We did look at this, and the genetic component making up morning or evening preferences is relatively small, so around 10%. So that indicates that this behaviour is modifiable, but at this stage we think it's too early to really say that we should advocate that women, for example, get up earlier, and we need to try to make this distinction between what it is about morning preference compared with actual behaviour, because there is some argument to say that individuals who have a tendency towards an evening preference, by disrupting that, by making them get up early, actually that could lead also to increased risk, because there's a sort of misalignment between their biological clock and their kind of social clock, as it were.
What is next for you and your group? What's the next plan?
So there is evidence to suggest that our body clock is also potentially important for other conditions and other diseases. And other types of cancer have also been suggested to be potentially impacted by these various sleep-related exposures. So we're going to also hopefully look at other types of cancer and also other types of diseases using the same type of methods that we've been applying in this study and look at those particularly on risk of disease.
Rebecca Richmond, she was speaking with Adam Murphy, and that work has just been presented at the National Cancer Research Institute's Cancer Conference in Glasgow.
Another reason to feel bad about my lions. And finally in the news, neonicotinoids are the world's most popular pesticides, and they're often added to seeds so that as plants grow, they're protected from insect attack. But the chemicals also get into the plant's nectar, meaning that harmless insects like pollinating honey and bumblebees are inadvertently exposed too. This affects the bees' foraging behaviour. But what about their behaviour when they get home, inside their nest? Well, no one knew, but now Harvard scientist James Krul has developed a way to tag individually an entire nest of bumblebees so he can follow what happens to their behaviour when they're exposed to neonicotinoids. And as Chris heard, it's not good news.
Neonicotinoids mimic chemicals that work in the insect's central nervous system, and they were developed in the late 80s and came into the market in the 90s and now really widespread. They're the most common group of insecticides used across the globe. And over the past few years, we've realized more and more these compounds, even at low levels, they're still having negative impacts on bees. So what we were interested in understanding is a little bit more of why that might be happening. And in the past 10 years or so, we've got a really great understanding now of the ways that these compounds affect foraging behavior. But what's going on inside of the nest, all this important behavior within colonies, has really been kind of a black box. And so what we wanted to do in our work is understand what these compounds are doing to that social life of the colony within nests.
Is that easy to do?
Yes and no. So it's easy if you're willing to have a few angry bees in the face. It's easy enough to open up a colony and look inside of it. One of the challenges of watching individual bees is it's really hard to scale up in a few different important ways. So one is it's, of course, hard to focus on 100 different things at once. So if there's 100 bees in a colony, it's really, really hard to understand what every one of those is doing at the same time. It's also really hard to do it for long time periods. And it's also really hard to do across multiple colonies. And so what we wanted to do in our work is get some automatic tools that let us do that work without having to look by eye. What we do is outfit every bee in the colony with a special little paper backpack, sort of like a very simple QR code that we've made really simple so we can make it really small and just glue it to the back of a bee. That lets us look inside of the nest with a camera and identify the location and movements and interactions of uniquely identified workers automatically without having to look by eye.
So basically, all the bees are tagged, and a computer via a camera can watch where individual bees go and what they do. And presumably then you can compare bees that are exposed to pesticides and those that aren't. And you can ask that crucial question, does this make a difference to how they behave?
That's exactly right. So one of the first things that we wanted to do with this technology of being able to look inside of a nest and follow what individual workers were doing is we pull out individual workers, feed them different amounts of a really common neonicotinoid pesticide called imidacloprid, and we can feed different amounts to workers that have been brought out of the colony and made a little bit hungry, so they're more likely to eat a little artificial sugar, and then we can put a controlled amount of this compound in that. And so within the same colony, we can feed different bees different amounts of the pesticide. And because we know the individual behavior of every bee in the colony, what we can look at is the changes in behavior within individuals. So is a specific worker acting differently and behaving differently than it was after we give them a little bit of this pesticide?
And is the exposure what we would dub field relevant? In other words, if these were bees in the wild and they were foraging in an area where a farmer had used some of this particular type of neonicotinoid, would the exposure that you're giving to them be equivalent to what they would probably encounter naturally?
Yeah, that's a great and really important question for this kind of work. The concentrations we're looking at are in the range that we expect to see in nectar and pollen in plants that have been treated months before as seeds with these compounds.
And when you do this, do you see a change in the way that the bees behave?
Yes, we do. So we see a couple different things change. So one thing is that workers within the nest move away from the nest center. So they seem to be a little further away from where a lot of the center of action of the nest is. They're also less active, and they also interact less with nestmates.
And do you think this makes a difference, though? Because some of these changes, they sound quite subtle. Does it make a difference to the fitness of the nest?
Yeah, we think it is likely to have important ties to colony function in the long run, even though we didn't directly look at that in this study. There's now a lot of other really great studies and great work showing that even these sort of same concentrations that we studied here can negatively impact the colony growth. And so we think these changes in behavior, for example, bees spend less time nursing and doing other kinds of nest care, all of those are really important for the growth of the colony. So this work suggests that we might be disrupting a lot of those other important behaviors within the nest and not just foraging.
So what should we do about this then? It sounds to me like we have pretty incontrovertible evidence that these compounds that are being routinely used are very disruptive to at least some species of insect. So can we justify continuing to use them?
I think that's a really important question, and I think at the very least, we certainly need to be having a very serious conversation about the role of these compounds in our food systems. We know for sure that these compounds can have negative impacts, but there's still huge open questions in terms of different species, how they vary over time and place. And so I think we need to be thinking very, very hard about the benefits that we get from using these compounds and what the clear risks are.
James Krall there, and that study has just come out in the journal Science.
And if you'd like to find out more about that or any of the other stories we've covered in the news this week, the transcripts and the references where relevant are on our website at nakedscientists.com.
The Naked Scientists podcast is produced in association with Spitfire, cost-effective voice, internet and IP engineering services for UK businesses. Find out how Spitfire can empower your company at spitfire.co.uk.
This is The Naked Scientist with me, Georgia Mills, and with Chris Smith. And before we get to the main part of the programme, we'd like to tell you about our fundraiser.
Yep, lots of you have been supporting us. I'm going to pick 5 names at random because there are lots and lots of you. So we've randomly selected 5 people. Christine Schmidt, thank you very much. Joel Rosner, thank you very much. Mark Hari, thank you very much. Roy Pembroke, thank you very much. And Insa Kroger, thank you very much. Those are 5 from many who have all supported The Naked Scientist in our fundraiser, nakedscientist.com/donate.
We really, really appreciate all the donations we've had so far, but we have a long way to go. We're actually trying to raise £50,000 for next year's programming, and this pays for things like studios, our people's time, equipment, or for when our computers explode.
Now, it does sound like a lot of money, but the good news is that if everyone listening to just one single episode of The Naked Scientist bought us a virtual cup of coffee by donating the equivalent of £3 to The Naked Scientist, then our running costs would be met for the next few years. So the way to do that is to go to nakedscientist.com/donate and pledge us a little bit of money. We would be really, really grateful.
And in fact, this week we've got a special show-themed giveaway running as well. If you go to nakedscientist.com/donate, you can donate any amount you can spare. And if you put hashtag I love the Naked Scientist onto the donor wall when you donate, you'll be put into a lottery to win a show-themed giveaway, which we'll be revealing later on in the programme.
And you've got to do that this week because we're going to select the people who do it within the next 7 days, and we will send you something extremely special. A Pearl Beyond price. These are unique. They've never been made before, they'll never be made again, and you've got the chance to have one of them.
Right, on with the programme. And this week...
Factories sprung up everywhere, making textiles, pottery, glass, bricks and metal goods of all kinds, from tin trays to steel knives.
After the first firing, there's inevitably little bits on the piece. There's alumina left on it.
This is the optical sorter machine. It's looking every kernel and decide to remove it or not.
There have been enormous changes in factory work in Britain. It has been totally transformed.
We're donning our overalls to drill into the science of manufacturing. And in order to forge ahead, first we need to know what manufacturing actually is. Well, Mike Gregory, former head of the Institute for Manufacturing here at Cambridge University, is here to help us. Hi, Mike. When we say manufacturing, what exactly are we talking about?
Well, we really mean a cycle of activities from understanding people's needs or wants, working out a design that will do that job, then working out how to make things and deliver them and service them, and to do all of that without using too much material or too much energy or without making a mess. And of course, in the middle of that cycle is the really interesting bit of making and shaping materials. I mean, how exciting can it be to dig up some materials, some earth out of the ground, fairly special earth, and turning it into an aeroplane. So that making bit is really exciting. But it's worth remembering that manufacturing is not just about planes and cars. It's about food and medicine and buildings.
And I know we have some food in the studio. I'm going to ask you about that in a second. But what are some of the common manufacturing methods that we use?
Well, there's a raft of them, and many of them you'll be familiar with. We can cast things into moulds. I wasn't thinking of cake necessarily, but cast iron. Or we can squirt things into moulds like plastics. We can extrude long strips of things through dies to make aluminium parts. We can bash things into shape by forging. Or we can machine them by cutting, either with machine tools or perhaps with lasers these days. And increasingly we can make things additively by adding on small amounts of material to make extremely complex shapes.
Right, so you're either sort of building things up, cutting things down, or just sort of bashing things together. Do we have much manufacturing going on in this country at the moment?
Well, we do quite a lot. There's a bit of a myth that we don't have any, hence the reason for your question, I suspect. But in fact, we're still the 6th largest manufacturer in the world. We have the 2nd largest aerospace industry. Rolls-Royce Aero engines are on 30% of the world's new aircraft. We make all the wings in this country for Airbus planes. All the major car makers have plants here, and we have global food industries, medicine industries, and these days a lot of attention being paid to making buildings in factories and assembling them together on site rather than putting one bit of clay on top of another as we do traditionally.
Oh, I'm imagining kind of flat pack house now. That's exciting. So what about robots? How have robotics changed our manufacturing efforts?
Well, as you appreciate, they don't look much like Star Wars robots. Really, they're there to move things around, and that's really useful. Jobs which can be very repetitive, which make us tired or sometimes pretty bored, can often be replaced by robots if they're reasonably standardised. And so a robot is a kind of automation. Doesn't have a head and arms, but it does have very accurate positioning capability and can work fast without getting tired or getting worn out.
Right, and Sam, who put the programme together, was telling me that even the most ordinary things have a good deal of robotics involved in them. I have here with me some Scotch pancakes. I'm going to open them and eat them while I'm asking you about them. Well, I would if I could open them, actually. That's quite
would you like me to help?
Chris, could you open them for me, please?
I'm offering because I'm hungry, actually. Right, here we go. Shall I resort to a key?
Maybe we should ask about the manufacturing of that packaging. It's quite...
Unopenable packet. I'm in. There you go.
Brilliant. Here we go. So Sam was telling me that even pancakes have robots involved in making them.
Well, it's a great example of robotic assembly. You tend to think of robots making mechanical parts, but really important for food because it's exactly that kind of process. It's very repetitive. You have to do it very fast and very reliably. And so that ring you see on the pancake is where the suction cup went on to pick the pancake up and put it on the assembly line.
It's the sort of ring you get if you imagine putting your cup down and you get a tea ring if you spill your cup on your desk. There's a ring that sort of size and shape on the surface of these little pancakes, and that's where the suction went.
Exactly.
So a little plunger just going blub, 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 picking up all the pancakes. Would you like one, Mike?
Have you got any butter to put on it?
No, I don't, I'm afraid. Just plain. Why are we still innovating in manufacturing? Don't we already know how to make things? Why is this important to invest in?
Well, although a lot of processes have been around for a long time, there's a lot we can do to make them better. So whether it's casting or forging, we can make them faster, we can make them cheaper, we can make them more accurate, and that's always worth doing. But of course there are new processes emerging, like additive processing that we mentioned before, and that will enable us to do things that weren't possible before and to do them in economical and practical ways.
I think it was Henry Ford who said, if you always do what you always did, you'll always get what you always got. So innovation is important. Mike Gregory, lovely to have you on the show. Thank you very much.
And we'll hear more about the importance of innovation later on in the programme. And undoubtedly one recent major innovation that's very important in the world of manufacturing is additive manufacturing. That also goes by the name of 3D printing. And the Manufacturing Technology Centre in Coventry has a team that are at the very cutting edge of this industry, and David Wimpenny is their chief technologist. David, why does additive manufacturing matter? Why is this a game changer in the industry?
It's so different than conventional manufacturing methods. And as Mike's already said, we're used to making parts by injection moulding, where the shape of a part is controlled by tooling, or by taking a block of material and machining away to form the shape. Now, both those techniques have drawbacks in terms of the waste of material that's formed, the geometrical flexibility, and the need to have fixed tooling. Additive is quite a simple technique. You're just depositing layer upon layer of material, one on top of another, but it allows unlimited flexibility in terms of the part geometry. And of course, another advantage is you can print parts on demand. You don't need to have the lead time and time to generate a mould tool, for example. And you can imagine a part that's being formed where across each layer can be a different distribution of materials. And layer by layer, that distribution can change. There is no process that I can think of that allows that flexibility and the potential that brings with it.
I was going to pick up on the point you made about making these things to order, because, of course, when we engineered or made things in the past, it was so expensive to make prototypes that often things were very, very slow to develop. But if you can 3D print things, you can try lots of different ideas very, very cheaply.
Absolutely. So your lead time between thinking of an idea and being able to bring it into production is very short now. And we have a whole raft of new companies where you've got an entrepreneur that's maybe even sat in his bedroom designing something, and the next day he could potentially be asking a company to print it. And he doesn't even need to have the printing equipment himself. The printing equipment can be based anywhere in the world. So this is flexibility we've never seen in manufacturing before. And of course, another advantage is that we can print things that are customised to individual people, printing things like customised implants for hip surgery. And also many people who've got dental work will have implants made for them, especially by 3D printing that match specifically what they need. So it's that flexibility we don't get with conventional manufacturing.
People are often familiar with 3D printers using plastic and things like that, but actually Rolls-Royce hit the headlines a couple of years ago when they flew a part in an engine which was the biggest flying 3D printed part. They'd printed a whole chunk of jet engine, and they used obviously metal for that. So tell us a bit about how we can use different materials in a 3D printing environment to make very specialist components.
So some of these materials, particularly in the aerospace industry, titanium alloy components are very commonly used. But it's quite a difficult material to process, so it's hard to machine, and it's also very expensive. So if you're using these more exotic materials, you don't really want to waste that material. And so additive manufacturing offers the potential to generate not just complex shapes, but also not to waste the material. You can add and also print the material exactly where you want it. So
how does it actually work, though? If I wanted to make a very complicated bit of engine out of a very costly material, how do I do it?
Yeah, that's a good question. So normally we'd take a fine powder, we'd lay it down in a very thin layer, and then we'd use a laser or an electron beam to selectively melt that powder to form a slice through the object. And then this process is repeated layer upon layer upon layer to effectively form the entire component. So it starts as a powder and ends up as a solid metal object.
Structurally, has it got good integrity? My reason for asking this is that I have been fortunate to go to Rolls-Royce's precision casting facility up in Derby, and they grow parts for their jet engines out of single crystals of the metal. So when they make the cast, they pour it into a very hot mould, and then they start this little crystallization process at one end of the object, and it spreads through the entire thing they're making, and that gives it enormous strength. If you're just fusing tiny little bits on each time, do you get the same single crystal, same strength that you would get?
We're struggling with single crystal at the moment. That's one area where there's still some work to do. But one thing we do get compared to, say, conventional forgings is that we can get really fine microstructure. So the material itself has better properties than you would get with some of the conventional manufacturing techniques, and certainly better than castings, where we're used to quite large defects in some cases for certain complex parts. So you are getting a better what we call a metallurgy from the materials you're using, but we're still struggling to get the sort of quality you get from a single crystal. But of course, in the future, we may not be utilising metals at all. We might be using ceramics, advanced ceramics, for these high temperature, high corrosion areas of a gas turbine. And as we increase the temperature, we get more efficient engines. Ceramics are very hard to form conventionally, so additive is yet another method to form these difficult to manufacture materials.
Well, that's very interesting, because I've not heard anyone talking about 3D printing with ceramic materials before. So what will that involve then? Because if you say that they're really hard to work with, why are they hard to work with, and how will we do this?
Well, typically ceramics are materials which are very brittle. They're difficult to shape, and one of the things we can do with additive manufacturing is we can take part materials in the form of powders and shape those materials. It also makes them less sensitive to cracking during the processing. So I've got colleagues working at the moment on using machines where we lay down a layer of fine ceramic material and we print a binder using an inkjet print head onto the material. That forms a sort of what we call a green component. It's effectively a loosely bonded ceramic component. That can then go through a process of being heated and fired in a furnace to make a fully dense component. And that really revolutionises the shape of parts that can be made by ceramics and also their potential to crack. There's also the potential to mix ceramic materials, which are very hard to process using conventional bulk ceramic manufacturing processes. So it could potentially revolutionise the ceramics industry, but ceramics is still lagging behind the plastics and metallic additive manufacturing processes because they've been around a little bit longer or more money's been dedicated to them. So ceramics is the next thing that's coming through, and we're starting to see really important developments in that area.
So what sorts of industries would you be talking to then? I can think medical for a start, because joint replacements might find a use for ceramics instead of metals, because people are worried about the wear particles of metals from, say, hip replacement. But what else?
Anything where you've got really high temperatures and you've got a corrosive environment, ceramics are really a big bonus. So applications for very high temperatures, again in aero engines, particularly space applications, we're seeing more interest in printing parts that are used in the rockets that send spacecraft into space. Require very, very high temperature materials, and often the current materials we've got can't really last long enough reliably, whereas ceramics, they've got that extra temperature resistance.
David, we must leave it there, but thank you very much for introducing us to the fascinating world that is additive manufacture. That's David Wimpenny. He's from the Manufacturing Technology Centre.
Still to come on The Naked Scientist, the manufacturing company trying to cut their environmental costs, and could you spot a Neanderthal baby in a lineup? Stay tuned. But first, since we were just talking about making very big things, let's flip the coin and consider making very, very small things. Sam Brown's been looking at manufacturing at the microscopic scale.
When you hear the word lasers, what do you think? Sci-fi battles in a space opera? Perhaps James Bond about to be cut in half? Well, while people have looked into these uses, really, lasers are much more commonly used for helping us make things rather than destroy things. This month, Samsung have announced their foldable phones, and the flexible electronics inside require powerful and precise lasers to cut and drill. So I, Sam Brown, took my phone with me to the Centre for Industrial Photonics at Cambridge University to find someone who could tell me which bits are already made using lasers.
Hi, my name is Dr. Francisco Orozco. I work here mainly using industrial processes that use laser as the main source.
Right, so you look like you're busy here. What's happening?
So today we're going to do a little bit of marking for you. So we're going to be putting the logo of the Naked Scientist into a little piece of steel for you. So what we're going to be looking at is a laser system that uses, let's say, very fast moving mirrors that reduces the area of the laser to a very small spot, talking around half the size of a width of the human hair. And then from there, the material that we're going to put underneath, which is stainless steel today, that will absorb the laser energy, and then it will heat up, and we will be able to remove some material, and then you'll see the Naked Scientist logo onto that piece of steel.
Oh, fantastic. It's behind quite a sturdy-looking safety screen. Why is this here?
We have a fully enclosed system, and the only way to look at the laser is through that little window. So that window reduces the intensity that the laser has, so you're able to see it. Otherwise, our eyes or our skin could get damaged from the laser.
Now that I felt sufficiently safe, we fired up the laser.
So right, let's kick this process off.
As the marking began, we could see the steel glowing brightly as it was heated. Dr. Orozco told me the maximum laser power being used was 1 kilowatt. That's 1,000,000 times that of a laser pointer you might have in a classroom, or use to play with your cat. But how exactly does a laser work?
All right, so the process that we're looking at here, the laser is focused down to a very small spot, and what it does, it will heat up the material, and it will remove some of the material by heat, and then the rest of it, you're basically going to have a change in the color, and that's what we're going to see today. So it'll remove a very thin layer, and then it will also heat up the metal, and that's why we have that marking, and that's why it's permanent, and you can remove it with your finger if you scratch it, because it's very durable, and it's hard to remove from the material.
And so where do I see this on my phone?
One of the applications that these sort of laser markers are used is for the marking of buttons or the logo of the company that sold you your phone. All those letters are basically made with a laser marker that's been removing a little bit of the material to give it a bit of contrast.
And what else is this used for, beside from phones?
Well, in industry, that will be used also for the dashboards on your car, all the digits that are there, your keyboards as well, laser marked for the clothing industry as well, so they're able to make the garments look like they're older or really make complex patterns with clothing, and they use a marker as well to remove the material and give you that finish that people like.
While the marker was running, Francisco led me to a room next door with an enormous table filled with shiny, polished mirrors and impressive-looking lenses.
Well, Sam, welcome to our ultra-fast laser facilities. We basically remove material using a very short pulse laser in this room. Just to give you an idea of time, that will be around a millionth of a second, give or take. So very short pulses. And what this does to the material, it does not create heat compared to the other laser that you've just seen today. So with the other laser, we usually create heat, and we have heat zones around where the high intensity laser hit the material, the metal in this case that we were looking at. And in this lab, this laser, the pulse is so short that heat doesn't dissipate to the material. So that is one of the main advantages of this process.
With the heat unable to spread, the material that is left won't be damaged or melted. It was for work on the generation of lasers of this kind that Donna Strickland and Gerard Mourou were awarded the 2018 Nobel Prize in Physics. These lasers are capable of making cuts that are less than a micron wide. That's smaller than the thousandth of a millimetre. But what does ultra-fast machining have to do with making parts for my phone?
Well, the laser is used to cut the glass that you have as a front screen, and it's also used to pattern the array that serves as a sensor for you to have a touch screen. Sometimes if you angle it right, you can see the little patterns on your phone, and basically that's done with a laser, because lasers are able to cut basically any material that you have, and it's really hard to do with any other processes.
So what makes lasers so good at doing these things?
Well, you have very tight tolerances. That means very high accuracy when you're cutting parts. Think of the spot of the laser being, again, a tenth of your hair or smaller, depending on which laser you use. So they're able to make very, very fine cuts, as well as there's like no vibrations where you're cutting glass that are very sensitive to that kind of things. You can really reduce the impact of machining and removing material basically from all these materials.
So what else do we use laser micromachining for?
Well, you have a lot of applications for these kind of lasers. So we can either add material or remove materials. It depends on what you want. For the health industry, so all the little stents are made via laser to machine the solar panels that you see in houses. If you go to the cutting edge of this technology, we have it being introduced for plastic electronics. So next generation devices that we're going to be having in the next years, this is one of the main processes and technologies that are going to be implemented.
So there's a host of uses, from medical implants to solar panels, for just this type of laser. Not to mention those used in other manufacturing applications like welding. Just before I left, Francisco had this fairly bold claim to add.
I'm pretty sure that anywhere where you are, you can see something that's been done with a laser.
Thank you, Sam. And Sam's actually with us in the studio now, so tell me, how similar to James Bond were these lasers?
Pretty similar. They would do quite serious damage to certainly your eyes, at least.
Could it burn through a table?
Yes, if you set it up wrong, it certainly could.
Well, we've actually got the fruits of your labour in the studio with us. It's the size of a credit card. It's made of steel, and it has 6 of the Naked Scientist logo printed on it. They're about the size of a penny each. And there's something rather unusual just above our little logo's head. It actually says something. It's a website address, and it's 1/10 of a millimetre high, and it says nakedscientist.com/donate, which brings us to our fundraiser.
Yeah, indeed. So we are trying to support our next year's programming and the ongoing maintenance of the Naked Scientists and development of the Naked Scientists website. So we've set up a donate page. It's nakedscientist.com/donate. Very special, exclusive to this week. Anyone who goes on and makes a donation this week and writes on our donor wall the following hashtag, what is it, Georgia?
Hashtag I love the Naked Scientists.
If you put that on the donor wall this week, then you have a chance to win the exclusive piece of merch that Sam made for the programme. That's unique. There's no other like it which has got those logos on it. But Sam, you very kindly volunteered to go the extra mile and do something for 10 other lucky donors this week.
Yes, we're going to mark up 10 of the same size pieces with the Naked Scientist logo on one side, and they'll be personalised on the other side with a name and a special thank you message for donating.
And what will it be in about 10 nanometre text? So you have no idea what it is.
That's a bit small. Maybe 100 micron text, so that's about the width of a human hair.
This is a unique piece of Naked Scientists memorabilia. And to get involved, go to nakedscientist.com/donate and put that hashtag when you make your donation. I love the Naked Scientists. And if your name comes out of the hat, we'll be posting you one. Thank you very much, Sam. Now, innovation, as we heard earlier, is very important for making new products, but it's also important for developing new methods of making the things we already have, but doing it in a more efficient and environmentally sound way. Mark Pickford is from the printing company Seacourt. They're based in Oxford, and they're winning awards for the environmental turnaround that they're bringing to the industry. So, Mark, what does Seacourt do?
Fundamentally, we're a printing company, so we're producing everything from stationery, letterheads, business cards, all the way through to corporate brochures, annual reports, sustainability reports. And we also manage a lot of work in terms of large format, so we're producing large format for events, pop-up stands and that kind of thing.
And why is the printing industry potentially a naughty player when it comes to the environment?
Well, 90% of printing that your listeners will be seeing on an everyday basis is produced by the lithographic process. It uses lots of water. Chemicals are added to the water, and those chemicals are very high in volatile organic compounds. As well as the industry is run on printing presses, very high users of electricity, generate a lot of waste, and it's something that we've kind of, as a business, decided that we needed to take responsibility for.
So basically the embodied energy and the embodied water in turning out something as trivial as a newspaper or even a sheet of printed paper is huge. And you want to try and change that.
Yeah, absolutely, yeah.
And how are you trying to address that?
We decided about 20 years ago to completely change the way that we did our business. And the first thing we looked at was the actual process itself. And so we converted going from the standard lithographic process to a waterless offset process, which basically eliminates the use of water. We've saved 8 million plus litres of water since we converted. We've completely taken out the chemicals that are added to the water to make it more usable for the process.
And to be clear, that water previously, given that it carried that toxic cargo, you couldn't just tip that down the drain. That would have had to have been
it's contaminated
remediated
water
in some way.
So you've got not only the contamination, but you also then have the power and the energy that you use to require to get it back to a normal usable process. So it's far-reaching.
Now, if this is so good, because I mean it sounds wonderful not to make all this contaminated water, not to use these other nasty chemicals, why isn't everyone doing this?
A few years ago it was going to be the next big thing, but the trouble is to get a printing company to convert to a completely different process, it can be financially ruinous. I mean, we were very lucky that when we decided to go down this route, that we were at a point where we wanted to develop the company. We were at a size where we could be flexible, but it requires completely changing the process, the machinery, the training of all your staff, the environment of the actual factory itself. So it's a very difficult process to suddenly go from one to the other.
So the capital outlay
is
very, very big. So
and
that
printing,
may be an impediment to smaller businesses.
Yeah, and to larger companies. The printing industry, like many industries, margins are very tight. There aren't great deals of money to suddenly invest on not producing anything for a month or 2 months while you convert to a completely different process.
So you've had to put up a lot of money to convert your process, but now you've done that, are you still competitive in the market? Can you still churn out print copy at a price that means you can compete?
Yes, we can. We have overheads that are slightly higher than another printing company, but the industry itself is on a race to the bottom in terms of pricing. So we would always argue that we are financially sustainable, which is just as important as the environment, if you like, as for a business. We certainly aren't the cheapest in the country, and we will never want to be, but we are very competitive. And we couldn't survive as a company in this market if we weren't competitive.
It's the sort of position that industry the world over finds itself in, isn't it, where the planet pays the price, where you end up, at the moment, we're all hooked on oil because it's cheap and it's there. And it means we can make stuff cheap. We make loads of plastic, for instance. It does the job we want. And at the moment, while the planet pays the price, we're comfortable to live with that. It means we've got to be brave and daring, spend some money and live with slightly higher production costs, but then the planet doesn't pay the price ultimately. And that's the sort of direction that you're taking, isn't it?
Absolutely, yeah.
So you've sorted out the water problem. What other initiatives or innovations are you looking to introduce in the future?
There's many things that we've done already, which is zero waste to landfill since 2009. Even our tea bags and sandwiches are dealt with by a team of worms, red tiger worms in the
They eat
business.
tea bags. I thought tea bags were a bit of a problem.
No, they seem to do absolutely fine on them.
Do they?
Yeah. I don't think they like garlic or onions. So we have to be a little bit selective about what we leave behind. But we've been running on 100% renewable energy for many years now. The whole process of the business is all about sustainability. We've looked at all of our staff, anything to do with the business and how they're engaged with the business, how they get to work. We go through carbon offsetting schemes. We always believe that mitigation is far more important than offsetting, so we mitigate it as much as we possibly can. And then what we can't mitigate, we offset through schemes in the Brazilian basin that involves local communities in the production of acai berries. So we have a social, economic and environmental benefit to the planet, whereby whatever we produce actually has a net benefit to the environment rather than a negative impact on the environment.
And did you notice, Mark, we've put you on the green microphone?
I did notice that, and thank you very much. It was noticed. Yeah, I was going to Bagsy it.
Mark Pickford is from Seacourt. Thank you, Mark. And I think there's a lot that other companies could learn from the trailblazing work that Seacourt have been doing. Thank you for joining us.
And to finish, still with us is Mike Gregory, former head of the Cambridge University Institute for Manufacturing. So we've heard about a lot of examples of exciting ways people are manufacturing things. But where is this all going? What do you think the future of manufacturing is going to look like?
Well, in some ways, it's going to be the same, but better. To get a glimpse of modern manufacturing, which we've had, is, I think, given a flavour of the excitement of making things, which isn't always obvious. Most of us don't get the chance to get inside factories. But we can see the products. So at home or on the way to work, in the office or the factory or the hospital, you can see the output of manufacturing all around you. And it's quite fun to think about how those everyday things have been made. And there's a lot of the world around us which can be made better by better manufacturing, making things cheaper, more reliable, more sustainably, so that we can bring the standards of living that we enjoy in the advanced countries to people all around the world. There's plenty to do. Manufacturing is not going to change, but it's going to get a lot better.
Very exciting times then. Thank you very much, Mike Gregory, and thank you to all of our guests. That's David Wimpenny, Francisco Orozco and Mark Pickford. And thanks to Sam Brown for putting the programme together.
And to finish this week, it's time for Question of the Week. And Sam has just been taking a trip back in time to answer this question from Stuart.
If you could bring a baby from the past to grow up in the present, how far back could you go before people would notice that this was a time-travelling baby?
Professor Robert Foley, Leverhulme Professor of Human Evolution at Cambridge University, provided us with this answer.
In evolutionary timescales, the answer is not very far. If we start the clock of human evolution at around 5 million years ago, when we split from our last common ancestor with chimpanzees, then probably up to around 200,000 years ago, we would begin to see quite big differences. Before that, not only would the babies look different, but they would grow more rapidly and develop faster.
So being shorter and hairier, we might be able to pick them from a crowd.
Yeah.
But what about behaviourally? Would they be able to function in today's society?
We don't know enough in detail about their behaviour to say if they would stand out today. They would have probably learnt to speak, but perhaps not with the range of syntax and vocabulary we have. An interesting reason why we can't be sure is that while people 200,000 years ago might not have had a developed language like us, it could be that they would have had the mental capacity to learn it in a modern cultural setting. We would probably have to go back to over 500,000 years ago to find them not speaking at all, perhaps the trait that would be most noticeable. It's a good question and echoes one I ask students. If we found a living Neanderthal child, should he or she be put in a school or a zoo? Probably school. But what about earlier modern ancestors, such as Homo erectus from 1 million years ago, or Australopithecines at 3 million?
Fascinating stuff, and another tricky question to finish off with too. But our forum users had even more to add. Halk suggests that one of the biggest challenges facing this time-travelling infant would be growing up in the first place. He says the baby will not have the benefit of the last, say, million years of perpetual evolution between us and the stuff that's trying to kill us. The baby would have a hard time growing up at all, since all these diseases that have bred to prey on humans will find the baby fairly defenceless. Well, we better start working on some vaccines alongside that time machine then. Next week, we'll be weathering the storm of uncertainty to answer this question from Norwich-based electrical engineer Daniel.
My question to the team is, why jet engines, the type you see on almost every commercial aeroplane with the large forward-facing fan blades, are not used on the aeroplanes that are sent to investigate hurricanes? These still use propellers, albeit that these may be driven in some way by a jet engine. Is it that propeller engines are safer in high-stress situations?
What do you think? You can email chris@thenakedscientist.com. You can find us on Facebook, you can tweet @NakedScientist, or join in the debate on the forum. And that's at thenakedscientist.com/forum.
Sadly, that is it for this week. The arrow of time has defeated us again. Do be sure to tune in next time, because we're going to be pondering the people of the future. What will Human 2.0 look like? The Naked Scientist comes to you from Cambridge University and is supported by the EPSRC and Rolls-Royce. I'm Chris Smith, and until next time, goodbye.